Our next property of Z transform is multiplication by exponent. So if xz is the Z transform of xn, then if you multiply xn by an exponent a to the power n, then its Z transform will be xz by a. So it can be expressed in terms of xz. Just we need to replace this z by z by a to find the Z transform of a to the power n xn. Okay, and also in the Z transform ROC for this a to the power n xn, we need to put z by a in place of z to find the ROC of the new signal multiplied by the exponent to the power n. So we can take this example of unit step signal discrete time un. So its Z transform is given by z by z minus 1. So a to the power n even formula we have used where a is equal to 1. So its ROC is mod z greater than 1. So if we put this constant here, exponent a to the power n un, then we have to write this z by z by a. So if we put that z by a in place of z, we will get this z by a, z by a minus 1, and this ROC is z by a greater than 1. So by simplifying this, we are getting z by z minus a, and the ROC becomes z by greater than equal to a. So this will be mod z greater than mod a. So we have written 1, it will be a. Next, so if we take this example e to the power un, same example we are taking, so we're extending this signal, unit step signal. So its Z transform is given by this z by z minus 1. So this is standard. Now if we do this time shifting operation here, so if we shift the time, then we meant to multiply by z to the power minus n naught to xz. So this is xz, so we have written here, and z to the power minus n naught is this n naught is this constant, so this is 4. So z to the power minus 4 multiplied by xz. So that is the Z transform of the previous signal. So now if we do the folding operation, that is we are taking minus n in place of plus n, then we have to divide, or we have to substitute z by z to the power minus 1 or z by 1 by z. So that we have done here. So since this z to the power minus 4 into z becomes 1 by z cube, so in place of this z cube we are putting 1 by z whole cube. Here also we are replacing that z by 1 by z, and due to this folding operation, negative value of minus n, this ROC becomes the reverse of the previous ROC, that is mod z is less than equal to 1 now. So if we now multiply this signal by t to the power n, so it is using the latest property, that is multiplication by an exponent, the a to the power n xn. So here what we do, we divide z by that constant. So if we do this multiplication by t to the power n, we need to divide this z by 3 here. So this 1 by z cube goes to the numerator and becomes z cube. So z cube, if we are writing for this, then we have to write z cube by z by 3. Due to this, we have to divide z by 3, so z by 3 whole cube. And in the denominator also, this becomes z. So it was 1 by z, so if we write here z by 3, then it will becomes 3 by z, so 3 by z minus 1. And also in the ROC we are writing z by z by 3. So as you see here, this mod z becomes less than 3 here, and by simplifying this we are getting z to the power 4 by 27 into 3 minus z. So this is the Z transform output for this signal. So we can find it starting from UN. We can do this time shifting operation and time reversal operation, then multiplication by exponent operation. Then you can go to obtain the exact or Z transform output for this signal. Okay. So the ROC also, it's starting from that we are going to modify the ROCs for each step, and finally the ROC will be updated. So in this approach we can solve the Z transform problems for these unit step signals or exponent multiplied signals. The next property is the frequency differentiation property or derivative in the Z transform property for Z transforms. So if xz represents the Z transform of xn, then we can write like this: n into xn is equal to minus z dt of xz. So derivative of xz multiplied by z minus z. So you can write like this. So if we do the shifting operation here, so why we are doing this shifting operation, if we put n minus 1 here, then you can multiply here by z to the power minus 1. So that z to the power minus 1 will be cancelled out with this z, and you can remove this z here by multiplying n minus 1 in the left hand side. So if you write n minus 1 into xn, so we're actually multiplying n minus 1 means we're shifting this n by n minus 1. So that's why this z is cancelled out in the right hand side here. Next, if we alter this symbol n minus 1, if we write 1 minus n, then we'll get this minus symbol as plus. So that's why we're coming to this expression, that derivative of xz, which indicates the differentiation of frequency domain transform, or xz is the frequency domain representation and its derivative is dtz of xz. So this equal to the time domain version like given by xn multiplied with 1 minus n. So using this property also you can do the transform for different signals. Like if we take this ramp signal, then it is given by, in continuous time you write t into ut, in discrete time you write n into un. Okay, so now we know that the z transform for this un is given by z by z minus 1, and its ROC is mod z greater than 1. So if you multiply by n here, then you can write here minus z into ddz of xz. So xz is this one, so you can put here. So ddz of xz means derivation of this term you have to do u by v form, so that you can do, and you have to multiply by z. So if you do the derivation here, you will get like this. So after solving, you can write this z transform of n into un is equal to z by z minus 1 whole square. So now this is the z transform output for this signal, and the ROC of this you have to write like this, that it cannot be 1, because if it is 1 then this will become 0 and it will become infinity, and this cannot be also 0. Okay, because there is a numerator term z. So if we put directly 0, then it does not exist. So the inverse Z transform problems we can solve basically based upon this formula, I to the power n un by Z transform is z by z minus I. So here this z by z minus 3, z by z minus 6, this will directly give the time domain version like this. So if this is a, so I to the power n un means 3 to the power n un, 6 to the power n un, you will get directly, and this constant 3 and 4 can be multiplied in the outside. This ROC, okay, these are this simple simplification here. 3 to the power n plus 1 you can write here, 2 to the power 2 into 3 you can write here, 2 into 2 for 4, so here 2 into 3. So you can divide these two terms like 2 to the power n plus 2 and 3 to the power n. So if you take common for this 3 to the power n un, then you can write here 2 to the power n plus 2 plus 3. So this is the expression for like the time domain signal of this exit. Now based upon the ROC portions, different portion of the ROC, we can divide this time domain signal in different expression. Like for mode z greater less than 3, so n will be negative, or for this part mode z less than 3 means this less than 3 means all values are negative, for because this is greater than 3, this is greater than 6. So if you are taking mode z less than 3, so all n values will be negative. So that's why we are putting here minus 3 in front of this, and we are putting minus n. Similarly here in front of this 6 we are putting minus, and also for minus we are putting for this n below. So when we are moving to the region 3 less than this will be less than symbol here, there will be, so 3 less than mode z less than 6. So in that region, so your one signal is like mode z greater than 6 and mode z is less than 6 and mode z is greater than 3. So mode z greater than 3 will include this ROC, and mode z less than 6 will not include this ROC. So this will become negative and this will become positive. So that's why we can write this positive and this negative time signals. So when mode z greater than 6, it will include both the signals in positive terms. That's why we can write like this. Next, the finding of inverse Z transform using long division property of procedure. We can do the inverse Z transform for the Z by Z minus Z. So we already know that this is the transform of a to the power n even. So how can we can derive that? So you can try like this. So if you divide Z by Z minus A, then you can write like this. So if you have to multiply with 1, then you will get z minus a. So z cancel, you will get a here. So if you want to find a, then you need to multiply this z minus a by z, then only z will be cancelled, you will get an a. So if you multiply this a by z with this, then you will get a minus a square by z. Similarly, you will get here a square by z, then again you take this coefficient and multiply. So this way you can go on dividing, and you will get a series like this as a result. So if you take this series here, so xz can be written like this. Okay, so if you take az inverse, and here also az inverse whole square plus az inverse whole cube, like this it goes. So the coefficients you can see here. So we know that z minus 1, this a to the power n series going on, a to the power 0, a to the power 1, a square, a cube, like this it goes on. So you can write a to the power n in generalized form, and un you can write as the z transform like z by z minus 1. Okay, so that's why we can write like this. Next, if you want to find a causal signal in time domain, then you have to rearrange this z expression, z or z terms in descending order of their power, like this. Okay, and if you arrange them in ascending order, then you will get, or they are in ascending order, then you will get an anti-causal signal. You can make this ascending order by taking the highest value out, and you can get in the negative powers ascending values. Okay, so if xz is equal to nz by dz, it is independent of poles. Long division method will give only two sequences. Okay.